The Materials Center Leoben is part of the ecsel joint undertaken project Power2Power. Within a partner network of 43 organizations and in close cooperation with Infineon Dresden, we analyzed newly developed high-power semiconductors with high energy efficiency. These devices are used in applications for mobility or heavy industry. The high-power electronic components consist of consecutive layers which have thicknesses in the nanometer range. To guarantee reliable applications which can handle the applied high electrical power, knowledge about the thermomechanical properties has to be generated. Our challenge was to characterize these nanometer thin layers with high resolution mechanical and thermal methods. For the mechanical characterization of the multi-layer system, we use the ion beam layer removal method. Within this method, a micro cantilever is cut. Then around 10 nanometer thin slices are removed from the cantilever. With these material slices, the residual stress is also removed, and from the change of the cantilever deflection, the residual stress can be reconstructed. With this method, regions with high residual stresses can be detected. This knowledge allows an optimization of the layer design in terms of stress engineering and crack stopping properties. To get a holistic understanding of the high-power electronic components under operation, it is essential to know the thermal properties of the multi-layer system. By knowing the thermal conductivities and the thermal interface resistances, a realistic temperature field of the operating device can be computed. With the scanning thermal microscopy, it is possible to map the thermal conductivities with a high resolution down to 50 nanometers. By scanning over the cross-section of the high-power device, an image of the thermal conductivities of the layer stack was generated. In addition, the time-domain thermal reflectance measurement is an optical method where a laser is used to catch the heat dissipation through the layer system. By consecutive measurement of different layer systems, the DDDR can detect the thermal diffusivity of the individual layers and the corresponding thermal interface resistances. The combination of both methods enables an accurate thermal characterization at the nanoscale to study the impact of the heat transfer in the engineered system. By provision of this measured data to our partners in the Power2Power project, we support them to reconstruct the temperature field and the stress profile of the devices under operation. In that way, we optimize the reliability of advanced high-power semiconductors.